What if everything you know about time is an illusion? Picture this. A single step into the unknown could take you not only to a distant star, but also to a distant era, past or future. And what if the gateways to these journeys are hidden in the most mysterious objects in our universe, black holes? Today, we're venturing into a mind-bending exploration of 30 groundbreaking theories that intertwine the concepts of time travel and black holes, unraveling the cosmic enigmas that defy our understanding of reality. From the warping of space-time to the possibility of alternate universes, this journey will challenge the limits of imagination and science alike. Buckle up, because by the time we're done, you might start to see time itself as less of a straight line and more of a vast, interconnected web, with black holes as the enigmatic anchors of this cosmic puzzle. Keep watching and prepare to have your perception of the universe forever transformed. Now turning to Einstein's groundbreaking contribution to our understanding of the cosmos, his theory of general relativity is where our journey truly begins. This theory revealed that space and time are not separate entities, but are interwoven into a single fabric known as space-time. Imagine space-time as a flexible sheet that can stretch, bend, or even warp under the influence of gravity. Massive objects like planets or stars create curves and dips in this sheet, much like how a heavy ball placed on a trampoline causes it to sink. These distortions in space-time explain how gravity works and set the stage for something even more astonishing: the concept that time itself can be influenced by these curves. According to Einstein, the stronger the gravitational field, the more space-time warps, and as a result, time slows down. This phenomenon, known as gravitational time dilation, is not just theoretical. It has been observed in real-world experiments involving satellites and atomic clocks. The implications of this are profound, as they hint at the possibility of manipulating time by harnessing these effects. Coupled with the extreme warping of space-time near black holes, this theory provides the essential framework for many of the time travel concepts we'll be exploring. So, with this foundational understanding in place, let's venture deeper into the possibilities that Einstein's insights have unlocked. Moving forward, let's delve into the fascinating concept of wormholes, often imagined as cosmic shortcuts through space-time. Picture space-time as a vast, stretched-out sheet of paper with two distant points marked on it. Rather than traveling straight across the paper, a wormhole metaphorically folds it so that these 2 points touch, creating a tunnel that bridges the gap instantly. These theoretical tunnels, known formally as Einstein-Rosen bridges, could, in principle, connect not just two locations in space, but also two different moments in time. If such a wormhole existed and was stable enough, it might allow someone or something to traverse vast distances or leap through time almost instantaneously. The allure of wormholes lies in their potential to make the impossible possible, traveling to a distant galaxy or even visiting the past or future. However, they remain purely speculative. The mathematics behind wormholes suggests they could exist, but their creation and stability would likely require exotic matter, a substance thought to possess negative energy density. This negative energy might counteract the intense gravitational forces trying to collapse the wormhole. Yet, exotic matter itself is a theoretical concept and has not been observed in nature. Additionally, even if wormholes were feasible, the implications of traversing one, such as paradoxes or disruptions to causality, raise profound questions. So, while wormholes ignite our imagination and feature prominently in science fiction, they remain an unresolved mystery. With this tantalizing possibility in mind, let's explore how the warping of space-time near black holes leads us to our next theory, time dilation. Now turning to the concept of time dilation near black holes, prepare to have your perception of time turned upside down. Imagine for a moment standing on the edge of a black hole, a region of space where gravity is so extreme that it bends not only light but also time itself. In the realm of physics, this phenomenon is elegantly explained by Einstein's theory of general relativity, which tells us that massive objects like black holes warp spacetime. This warping creates a striking effect. Time moves slower the closer you are to a strong gravitational field. To better understand this, think of the movie Interstellar, where the characters visit a planet close to a supermassive black hole. Due to the immense gravitational pull of the black hole, time for them on the planet slows down dramatically compared to time experienced by someone farther away. For every hour they spend on the planet, years pass back on their spaceship. This isn't just science fiction, it's a scientifically grounded concept. Time dilation has been observed in smaller, real-world scenarios such as on Earth, where clocks positioned closer to sea level tick slightly slower than those located higher up. However, the time dilation near black holes takes this effect to an entirely new extreme. It poses an intriguing possibility for time travel, at least into the future. Picture orbiting a black hole for what feels like mere moments, only to return and find that decades or even centuries have passed for everyone else. Such journeys would, of course, come with immense risks, as the gravitational forces near a black hole could easily tear apart anything that gets too close. And yet, this profound relationship between gravity and time remains one of the keys to unlocking the mysteries of the universe. With this in mind, let's take a step further and unravel the daring hypothesis that black holes might not only warp time but also serve as gateways to other universes. Moving forward, let's explore an extraordinary idea that shifts our understanding of black holes from cosmic traps to potential gateways to other universes. This daring hypothesis suggests that instead of simply swallowing everything in their vicinity, black holes might serve as portals to entirely separate realities. Imagine a doorway leading not just to another part of our universe, but to a completely different universe altogether. This concept finds its roots in quantum physics and the ever-fascinating multiverse theory, which proposes that our universe is just one of countless others coexisting in a vast multiversal landscape. A clue to this possibility lies in the enigmatic nature of black hole singularities, the point at their core where gravity becomes infinite and the known laws of physics break down. It is here some researchers propose that the boundaries of our universe might intersect with those of another. Adding to this intrigue is the idea that the immense gravitational forces and extreme warping of spacetime within a black hole could theoretically create a tunnel, a bridge often referred to as a wormhole, connecting one universe to another. While wormholes remain purely theoretical, mathematical models based on Einstein's theory of general relativity suggest such phenomena could exist. Further supporting this possibility, quantum mechanics hints at the interconnectedness of particles across vast distances, raising questions about whether such entanglements could extend across universes. If black holes truly are gateways, they might hold the key to understanding not just our universe, but the entire multiverse. However, even the most daring scientists acknowledge that this is all speculative. Crossing into another universe, if it were possible, would involve navigating unimaginably extreme conditions that could obliterate any object attempting the passage. Yet, this hypothesis continues to inspire and challenge the way we think about the cosmos. With this thought-provoking idea lingering in our minds, let's dive into the philosophical puzzle of time travel, the famous grandfather paradox, and how black holes might complicate or even offer a solution to this timeless conundrum. Now turning to one of the most compelling puzzles in the realm of time travel, the grandfather paradox presents a fascinating challenge to our understanding of causality. This thought experiment poses a seemingly insoluble dilemma. If someone were to travel back in time and prevent their own grandparent from meeting their partner, this action would effectively erase the time traveler's own existence. Without their existence, however, how could they have traveled back in time to cause this event in the first place? It is a loop of contradictions, raising profound questions about the nature of time, free will, and the fabric of reality itself. But how do black holes fit into this paradox? Some theories propose that the extreme warping of spacetime near a black hole could create conditions where timelines might split or diverge. In this scenario, altering the past could result not in the erasure of the time traveler, but in the creation of an entirely new timeline, one where the effects of their actions unfold independently of the original universe. This concept aligns with certain interpretations of quantum physics that suggest parallel timelines or branching universes might exist. If true, it could mean that black holes, with their immense gravitational forces and potential to distort spacetime, might act as catalysts for these alternate realities. On the other hand, black holes might also serve as barriers, trapping any changes made to the past within their confines, effectively isolating them and preventing causal paradoxes from spilling over into the broader universe. While these ideas remain speculative, they highlight the tantalizing possibility that black holes could offer solutions, or at least intriguing complications to the grandfather paradox. As we ponder this mind-bending interplay between time travel, causality, and black holes, our journey continues to uncover even more enigmatic phenomena. Let us now delve into Stephen Hawking's groundbreaking theory of black hole radiation and its profound implications for the concept of eternal black holes and potential time travel. Moving forward, we arrive at one of the most revolutionary ideas in the study of black holes, Stephen Hawking's theory of black hole radiation. Traditionally, black holes were thought to be eternal entities, consuming anything that ventured too close and trapping it forever. However, Hawking's groundbreaking work turned this notion on its head. He proposed that black holes are not entirely black, but instead emit tiny amounts of radiation, now famously called Hawking radiation. This radiation arises due to quantum effects near the event horizon, the boundary surrounding a black hole from which nothing is supposed to escape. According to the theory, pairs of virtual particles constantly pop in and out of existence in the vacuum of space. When this happens near the event horizon, one particle might fall into the black hole while the other escapes, creating the appearance that the black hole itself is radiating energy. Astonishingly, over immense stretches of time, this process would cause black holes to lose mass and eventually evaporate entirely. This discovery carries profound implications not only for the fate of black holes but also for the very fabric of the universe. In the context of time travel, Hawking radiation raises intriguing possibilities and challenges. If black holes are not eternal, any hypothetical time travel device relying on their stability might face significant limitations. For instance, entering a black hole as part of a time travel journey might lead to unexpected outcomes if the black hole is gradually evaporating. Additionally, as black holes shrink and radiate energy, the extreme warping of spacetime near them could change, potentially altering the pathways or conditions theorized to enable time travel. Furthermore, the evaporation of black holes also intersects with the mysterious information paradox. If black hole evaporation truly erases all information about what has fallen into them, this might disrupt our conventional understanding of cause and effect, complicating any theories of time travel that rely on predictability and consistency. Yet, some physicists argue that the information trapped within a black hole could re-emerge as the black hole evaporates, perhaps encoded within the radiation itself. If true, this might unlock a new layer of understanding about time, entropy, and the interconnectedness of past, present, and future. As scientists continue to explore these extraordinary ideas, one thing remains clear. Hawking's insights reveal black holes to be dynamic and enigmatic, challenging assumptions at every turn. With this, we now venture deeper into the cosmos and consider the role of cosmic strings and their potential to create time loops in the fabric of spacetime. Now turning to the fascinating concept of cosmic strings, we dive into a hypothesis that stretches the imagination to its limits. cosmic strings are theorized to be incredibly thin yet immensely dense defects in the fabric of spacetime, thought to have formed in the earliest moments of the universe's existence. These one-dimensional structures, if they indeed exist, carry an extraordinary amount of energy and could warp spacetime in mind-bending ways. Imagine two cosmic strings coming close to one another, or a single string looping back on itself. The immense gravitational forces they generate could theoretically distort spacetime so drastically that they create closed time-like curves. These curves would, in essence, form loops in time, potentially making time travel to the past or future possible. However, while this theory is tantalizing, the practical challenges it poses are monumental. For one, the energy levels required to maintain such a spacetime configuration would be almost incomprehensible, far exceeding anything our current technology can harness. Additionally, exotic materials might be necessary to stabilize these loops and prevent them from collapsing, materials that remain purely speculative at this point in our understanding. Even with these obstacles, cosmic strings capture the imagination of physicists because they highlight the interconnectedness of quantum mechanics, general relativity, and cosmology. They push the boundaries of what we know about the universe's structure and how it might be manipulated. If cosmic strings were ever observed or their existence confirmed, it could revolutionize our approach to the science of time and space. While we are far from achieving the technological advancements needed to experiment with such possibilities, the ideas inspire new ways of thinking about the cosmos and humanity's place within it. With this thought-provoking theory in mind, let us now venture further into the enigmatic world of closed time-like curves and uncover how spacetime itself might fold back on its own timeline, offering yet another pathway to understanding the mysteries of time travel. Now turning to the intriguing concept of closed time-like curves, we step into a realm where spacetime itself bends so profoundly that it loops back onto its own timeline. These curves are theoretical solutions predicted by Einstein's equations of general relativity, and they represent paths through spacetime that could allow an object, or even a person, to revisit past moments or venture into the future. Imagine tracing a circle not on a flat surface, but within the very fabric of spacetime, where the end of the circle connects directly to its beginning. This is the essence of a closed time-like curve. One of the most compelling aspects of these curves is their potential connection to black holes and wormholes. For instance, certain types of rotating black holes known as Kerr black holes are hypothesized to create conditions where closed time-like curves might emerge. Their rapid spinning could twist spacetime in such a way that paths through time become closed loops, theoretically enabling time travel. Similarly, some wormhole models suggest that if one end of the wormhole experiences a different passage of time due to gravitational effects, a closed time-like curve could form between the two ends. However, these possibilities are not without challenges. Closed time-like curves introduce profound questions about causality. If one were to travel back in time via such a loop, could they alter events in a way that creates paradoxes, such as the famous grandfather paradox? The very existence of closed time-like curves also poses questions about whether the universe has mechanisms, such as Hawking's chronology protection conjecture, that inherently prevent such paradoxes from occurring. Moreover, creating or stabilizing a closed time-like curve would require conditions far beyond anything achievable with our current technology. The energy levels involved, paired with the need for exotic matter to stabilize these configurations, place these concepts firmly in the realm of theoretical physics for now. Yet, the idea of closed time-like curves continues to inspire scientists and thinkers as it pushes the boundaries of what we understand about time, space, and the fundamental nature of reality itself. As we unravel the layers of this mind-bending theory, let us step deeper into another captivating possibility, the information paradox, and explore what happens when information interacts with the mysterious depths of black holes. Moving forward, we delve into the intriguing realm of the information paradox, a conundrum that continues to baffle physicists and challenges our very understanding of the universe. When an object falls into a black hole, it carries with it information about its physical state, such as its composition, shape, or quantum characteristics. According to the laws of quantum mechanics, information about a system can never be destroyed. However, black holes, as described by general relativity, are said to trap everything that crosses their event horizons, seemingly erasing any trace of the information once it falls inside. This contradiction between quantum mechanics and general relativity forms the core of the information paradox. What happens to this information? Does it disappear forever, or is it somehow preserved within or beyond the black hole? One proposed solution comes from the concept of Hawking radiation, which suggests that black holes gradually lose mass and energy over time, eventually evaporating completely. But this raises yet another dilemma. If the black hole vanishes, what becomes of the information it once contained? Does it escape with the radiation, or is it irretrievably lost? Some theories suggest that the information might be encoded in the radiation itself, though in an extremely scrambled form that would be nearly impossible to reconstruct. Others propose that the information could remain on the event horizon, stored on a two-dimensional surface, a concept aligned with what is known as the holographic principle, which posits that the three-dimensional contents of a black hole might be represented as a sort of hologram on its surface. Alternatively, some physicists speculate that black holes might function as gateways to other universes, where the information is transferred rather than destroyed. However, such ideas remain purely theoretical and unproven. The resolution of the information paradox is not just about understanding black holes. It has profound implications for time, causality, and the fundamental laws governing our universe. If information is indeed lost, it would force us to rethink the principle of determinism, where the future is always determined by the past. If information can simply vanish, it opens up profound possibilities that defy our conventional notions of cause and effect. On the other hand, if information is preserved in some form, it might hold the key to unifying quantum mechanics and general relativity, two pillars of modern physics that remain incompatible. The information paradox remains one of the most compelling mysteries in theoretical physics, pushing us to question what we know about the universe and perhaps redefine the very nature of reality. With this enigma in mind, let us journey further into the fascinating idea of the exotic materials and negative energy required to stabilize such theoretical constructs as wormholes and their potential role in time travel. Now turning to the fascinating concept of exotic matter and negative energy, we explore their crucial role in the theoretical stabilization of wormholes, those hypothetical shortcuts through space-time that could potentially enable time travel. Unlike the ordinary matter that makes up everything we see around us, exotic matter is theorized to possess properties that defy the normal rules of physics. One of its most intriguing characteristics is negative energy, a concept that directly challenges our intuitive understanding of how energy works. Negative energy isn't just less energy. It represents a reversal of the kind of energy we are familiar with, allowing for effects that ordinary matter and energy simply cannot achieve. This is where it gets interesting. To keep a wormhole open, preventing it from collapsing under the immense gravitational forces pulling it shut, it's believed that negative energy would act as a counterbalance, essentially propping the wormhole open like cosmic scaffolding. However, there's a catch. Exotic matter with negative energy isn't something we can simply gather or create in a laboratory. While quantum mechanics predicts the existence of fleeting, negative energy states in certain conditions, such as near black holes or within the framework of the Casimir effect, these instances are extraordinarily tiny and far from being usable on a meaningful scale. Theoretical physicists argue that sustaining a stable wormhole would require a vast amount of negative energy, far beyond anything we've ever observed or could reasonably harness with our current understanding of physics. Even the generation of small amounts of negative energy remains a colossal challenge, requiring conditions and technologies that are at best speculative and at worst unattainable. The need for exotic matter also introduces profound questions about its nature. If it exists, how did it form? Could it be created through some as yet undiscovered quantum process, or does it reside in the far reaches of the universe, waiting to be found? Furthermore, the presence of negative energy might have broader implications beyond wormholes, potentially playing a role in the expansion of the universe or even in explaining dark energy, the mysterious force driving the universe's accelerated growth. But for now, the existence of exotic matter and negative energy remains firmly in the realm of theoretical speculation, a tantalizing puzzle that beckons us to push the boundaries of our understanding. As we grapple with the mystery of exotic matter, we move into the realm of black hole singularities, points where the fabric of spacetime itself breaks down, revealing even deeper enigmas about the nature of time. Now turning to the enigmatic concept of black hole singularities, we delve into the very heart of these cosmic phenomena where the rules of spacetime as we understand them completely collapse. A singularity is theorized to be a point of infinite density, where the gravitational forces become so immense that the fabric of spacetime is stretched to its limits and then shattered. At this point, the known laws of physics no longer apply, leaving us with profound questions about the nature of reality itself. Imagine spacetime as a flexible sheet. A black hole with its incredible gravity pulls this sheet down into a steep well, but at the singularity, it's as though the sheet has been punctured entirely, creating a region where not even the concept of space and time remains intact. This breakdown means that within the singularity, time could essentially lose all meaning. It might cease to exist as a measurable dimension, or alternatively, it could reset entirely, creating possibilities that defy our current understanding of causality and the progression of events. Some theories even suggest that singularities could act as gateways to new universes, where time begins anew in a completely different form. But this leads to deeper questions. If time can reset or disappear at singularities, does this mean that time itself is just a construct, bound to the physical conditions of the universe? Or could there be a deeper, more fundamental layer of reality where time operates differently? Singularities also challenge us to reconsider the flow of time. If time can break down or restart, what does this mean for the arrow of time, the forward progression that governs everything from the aging of stars to the ticking of a clock? Could these cosmic points hold the key to understanding why time moves in one direction, or might they reveal a way to reverse its flow entirely? While the concept of singularities raises endless possibilities, it also underscores the limits of our current knowledge. Without a unified theory that combines general relativity and quantum mechanics, we are left with only fragmented glimpses into this utterly alien realm. Yet, studying singularities could bring us closer to unraveling some of the deepest mysteries of the universe, including the true nature of time itself. As the mysteries of singularities continue to challenge our understanding, we now explore a theory that takes us beyond our own universe, suggesting that black holes could be the ultimate connections to parallel worlds through the lens of the multiverse theory. Now turning to the multiverse theory and its fascinating connection to black holes, we enter a realm of possibility that stretches the imagination. The multiverse theory proposes that our universe is just one among countless others, each with its own unique laws of physics, timelines, and realities. Black holes, with their extreme gravitational forces and mysterious inner workings, are thought by some researchers to act as bridges or portals between these alternate universes. Imagine a black hole not as an endpoint but as a cosmic doorway, an entryway to a completely different reality where time unfolds in ways we cannot comprehend. According to this theory, when matter falls into a black hole, it might not simply be destroyed or lost forever. Instead, it could be transported into a new universe where it contributes to the formation of entirely new stars, planets, or even galaxies. This idea aligns with the speculation that black holes could fuel the creation of baby universes, smaller universes branching off from ours and growing into independent realities. If black holes truly connect us to alternate universes, they might also provide a pathway for time travel. By entering a black hole and emerging in a parallel universe, one might encounter a timeline that operates differently from the one we know. For example, time could run backward, forward at an accelerated rate, or even in loops, creating scenarios that challenge everything we think we understand about causality. Furthermore, the multiverse theory raises profound questions about the choices we make and their consequences. If parallel universes exist, each decision we take could spawn a new timeline, branching off to form a new reality. Black holes, in this sense, might be the threads weaving together these countless timelines, offering a glimpse into the infinite possibilities of existence. But with all its intrigue, this theory also highlights the immense unknowns surrounding black holes. Could we ever truly traverse a black hole to another universe, or is this merely a thought experiment without physical possibility? While current technology and understanding cannot confirm the existence of these cosmic bridges, the multiverse theory continues to inspire some of the most imaginative and groundbreaking discussions in both physics and philosophy. With these exciting ideas about black holes and their potential as gateways to parallel dimensions, we turn our attention to another tantalizing aspect of their nature: how the immense gravitational lensing caused by black holes can distort spacetime and create phenomena that challenge our perception of time itself. Now turning to the concept of extreme gravitational lensing, we encounter one of the most mind-bending effects of black holes. The immense gravitational pull exerted by a black hole is so powerful that it doesn't just affect matter, it also warps spacetime itself. This warping creates a phenomenon known as gravitational lensing, where light traveling near a black hole is bent and distorted, much like how a glass lens bends and focuses light. Imagine observing a distant star through the influence of a black hole's gravity. You might see multiple images of that same star, a ring of light, or even unusual streaks and arcs that result from the bending of light around the black hole. But gravitational lensing doesn't just create stunning visual effects, it also has profound implications for our understanding of time. As light follows these distorted paths through the warped fabric of spacetime, it may take longer to reach an observer, effectively creating what seems like a delay or distortion in time. From this perspective, black holes act almost like cosmic funhouse mirrors, reflecting light and time in ways that challenge our perception of reality. Some researchers even suggest that gravitational lensing could allow us to observe events from the past, as the bending of light might reveal glimpses of long-lost stars or galaxies that existed billions of years ago. This connection between warped spacetime, light, and time opens up fascinating possibilities, not just for astronomy, but also for the study of time travel. Could gravitational lensing be a tool for peering into alternate timelines or observing the universe's history unfold in reverse? While these ideas remain speculative, the study of extreme gravitational lensing continues to provide valuable insights into the mysterious relationship between black holes, light, and time. As we explore these incredible phenomena, we're reminded of how little we truly understand about the universe. With this in mind, let's move forward to examine the arrow of time and how black holes might hold the key to bending or even breaking its forward march. Moving forward, let's delve into the concept of the arrow of time, a fundamental idea rooted in both philosophy and thermodynamics. At its core, the arrow of time represents the one-way direction in which time progresses from the past through the present and into the future. It's something we experience in everyday life, evidenced by simple phenomena like a glass shattering but never reassembling itself, or the way heat flows from a hot object to a colder one following the laws of thermodynamics. But what if this forward march of time isn't as fixed as it seems? Black holes, with their extraordinary gravitational influence, have the potential to disrupt or even manipulate this arrow. One way this could occur is through the immense entropy associated with black holes. Entropy, which measures the amount of disorder within a system, is a key driver behind the arrow of time. The second law of thermodynamics states that entropy tends to increase over time, aligning with our perception of time's forward flow. However, when matter falls into a black hole, the information it carries is seemingly lost, creating a paradox about what happens to that entropy. Does the black hole itself encapsulate this disorder, or could it somehow reverse the progression of time by violating the rules of thermodynamics? Additionally, some theoretical models suggest that black holes could act as regions where time behaves unpredictably. Near the event horizon, where the gravitational pull is so strong that even light cannot escape, time for an outside observer appears to slow down dramatically. From this perspective, one might argue that the arrow of time bends or warps under the influence of a black hole's gravity, creating scenarios where the distinction between past, present, and future becomes blurred. Could such extreme conditions offer clues about reversing time or stepping outside its traditional boundaries? While these ideas remain speculative, they underscore just how intricate and mysterious the relationship between black holes and time truly is. As we continue to question the nature of time itself, let's dive deeper into the quantum realm to uncover how it might help unlock secrets of time travel. Now turning to the realm of quantum mechanics, we step into a world where the rules of classical physics start to blur, offering fascinating possibilities for understanding time travel. One of the most intriguing ideas is the concept of quantum entanglement. This phenomenon occurs when two particles become so deeply connected that the state of one instantaneously affects the state of the other, no matter how far apart they are in space. Imagine two particles at opposite ends of the universe communicating faster than the speed of light. This kind of instant connection challenges our understanding of time and causality. Could quantum entanglement be the key to creating shortcuts through time, or even bypassing time as we know it? Another captivating idea involves particles called tachyons. These are hypothetical particles that, if they exist, would travel faster than light. Since Einstein's theory of relativity ties the speed of light to the fabric of spacetime, tachyons could theoretically move backward in time, opening a doorway to the past. While they remain purely theoretical, the implications of their existence are mind-bending, suggesting that, at the quantum level, time might not flow in the linear way we perceive. Black holes add yet another layer of complexity to these theories. The intense gravitational forces near a black hole not only warp spacetime but could also amplify quantum effects. Some physicists speculate that quantum fluctuations near a black hole's event horizon might create conditions where particles like tachyons, if real, could manifest. Could these extreme environments serve as laboratories for testing the limits of time travel? Furthermore, the paradoxes that arise with quantum mechanics, like Schrödinger's cat existing in both life and death simultaneously, hint at scenarios where multiple timelines coexist, a concept eerily similar to time travel narratives we often see in science fiction. If black holes can harness these quantum phenomena, they might hold the clues to unraveling the mysteries of not just time travel, but also the very nature of reality itself. As we ponder these quantum possibilities, our journey takes us toward another fascinating idea. What if the rotating power of black holes opens new avenues for exploring time? Let's explore this next. Now turning to the fascinating concept of rotating black holes, we encounter the Kerr black hole model, a theoretical phenomenon that redefines what we know about black holes and their potential link to time travel. Unlike static black holes, Kerr black holes are formed from massive stars that collapse while retaining angular momentum, causing them to spin at extraordinarily high speeds. This rapid rotation creates a unique spacetime structure around the black hole, described by physicists as a region of frame dragging. Essentially, the intense rotation warps spacetime, dragging it along with the black hole's spin. This leads to the formation of an ergosphere, a boundary outside the event horizon where spacetime itself is twisted so significantly that objects cannot remain stationary. What makes this model especially intriguing is the possibility of entering the singularity, the core of the black hole, without being completely destroyed by its gravitational forces. In theory, the centrifugal force generated by the black hole's spin counteracts the immense gravitational pull, creating a potential pathway that might allow matter or even information to traverse through the singularity. Many theorists have speculated that such a journey could connect one point in spacetime to another, effectively enabling time travel. But here's where it gets even more mind-boggling. Some physicists suggest that if you follow the right trajectory through a Kerr black hole, you might not just travel through time but also emerge in an entirely different universe. This leads to the tantalizing idea that rotating black holes could act as natural time machines, offering a route to both other eras and possibly other dimensions altogether. While this remains purely theoretical, understanding the physics of Kerr black holes gives us a glimpse of how the intense interplay of gravity, motion, and time could unlock new realms of possibility. With this concept in mind, let us now venture into another fascinating theory. What if black holes themselves represent a profound reversal of time? Moving forward, we encounter the fascinating notion of white holes, often described as the theoretical counterparts to black holes. While a black hole pulls everything, including light, into its dense core with an inescapable gravitational force, a white hole does the exact opposite. It is theorized to expel matter and energy, making it impossible for anything to enter. Imagine it as a time-reversed version of a black hole where instead of drawing everything in, it pushes everything out. This idea stems from solutions to Einstein's equations of general relativity, which suggest that if black holes exist, white holes might also be possible. But what truly captivates the imagination is the potential connection between the two. Some scientists hypothesize that black holes and white holes could be linked, forming a sort of tunnel through spacetime, a phenomenon more popularly referred to as a wormhole. If this were true, then a black hole could serve as an entry point while a white hole could act as the exit, potentially bridging two distant points in space and time. Such a connection not only fuels the dream of interstellar travel, but also raises intriguing ideas about time travel. Could a journey through a white hole lead someone into the distant future or even the ancient past? Could it open a gateway to an entirely different universe? While these questions remain speculative, the concept of white holes challenges our understanding of the universe's structure and the flow of time itself. Much like black holes, no direct evidence of white holes has been observed, and their existence remains a theoretical construct. However, they remind us that the universe may harbor phenomena far stranger than we can currently comprehend. With white holes expanding our conceptual boundaries of spacetime, let us delve further into the idea of how the universe might regulate itself against such paradoxes through Stephen Hawking's chronology protection conjecture. Now turning to Stephen Hawking's fascinating proposition known as the chronology protection conjecture, we explore an idea that seeks to safeguard the universe from the chaos of time paradoxes. At its core, this concept suggests that the laws of physics themselves may inherently prevent the possibility of time travel to the past, ensuring that paradoxes like altering key events in history cannot occur. Imagine, for instance, the infamous grandfather paradox, where traveling back in time to prevent the birth of your own ancestor would erase your very existence, creating a contradiction. Hawking's conjecture implies that such scenarios might be fundamentally impossible, as natural mechanisms within the fabric of space-time could intervene to block any timeline inconsistencies. One way this might manifest is through the formation of physical barriers, such as intense radiation or energy spikes, near regions where time loops could theoretically form. These barriers could render such time travel pathways unstable or outright unattainable. According to this idea, the universe essentially functions as a self-regulating entity, protecting causality and the logical order of events. While this theory remains speculative, it provides a compelling framework for why time travel into the past has not been observed, despite its theoretical feasibility in certain interpretations of general relativity. As we unravel these intricate possibilities, the chronology protection conjecture not only deepens our understanding of space-time, but also invites us to ponder the delicate balance of the universe's design. And with this protective mechanism in mind, let us journey further into the realm of relativity by examining the twin paradox and how it brings us closer to understanding time travel into the future. Now turning to the twin paradox, we unravel one of the most intriguing implications of Einstein's theory of relativity. This thought experiment presents a scenario where time dilation caused by traveling at speeds close to the speed of light leads to drastically different experiences of time for two individuals. Imagine identical twins. One remains on Earth while the other embarks on a journey through space at near light speed. Upon returning to Earth, the traveling twin would find that their sibling has aged significantly more than they have. This phenomenon, supported by experiments involving high-speed particles and atomic clocks, demonstrates that time can flow at different rates depending on relative velocity and gravitational strength. In the context of black holes, the immense gravitational pull near these cosmic giants slows time considerably for anyone venturing close to their event horizons, much like how the traveling twin experiences time differently. Such environments provide natural settings for this relativistic time travel into the future, as someone lingering near a black hole for minutes could return to find that years or even centuries have passed elsewhere. This paradox doesn't just challenge our perception of time, but also shows how the boundary between science fiction and scientific reality is thinner than we might think. And as the implications of time dilation continue to captivate the imagination, they set the stage for deeper explorations of how black holes could shape our understanding of time and space. Moving forward, we dive into the fascinating world of hypothetical time machines, a concept where theoretical science meets human imagination. Among the most compelling designs proposed by physicists is the Tipler cylinder. Imagine an infinitely long, spinning structure made of incredibly dense material. According to scientific calculations, if such a cylinder rotates fast enough, it could warp space-time around it, creating closed time-like curves. These curves theoretically allow someone to move through time, either into the past or the future. However, the practicality of constructing a Tipler cylinder is daunting. The materials required would need to be extraordinarily dense, and achieving infinite length seems impossible within the bounds of our universe. Then there are traversable wormholes, essentially tunnels through space-time connecting two distant points. If stabilized with exotic matter possessing negative energy, these wormholes could serve as pathways for time travel. Enter the role of black holes. Their immense gravity might naturally create or influence such wormholes. Some theories even suggest that spinning black holes, known as Kerr black holes, could harbor conditions conducive to creating these space-time shortcuts. However, each of these designs remains highly speculative, facing immense challenges like sourcing exotic matter or preventing destructive forces near black holes from annihilating everything that enters. While these ideas are far from practical reality, Their exploration inspires not only advancements in theoretical physics, but also questions about what limits, if any, truly exist in our understanding of the universe. With the next phase of the journey in sight, let's explore the cutting-edge world of black hole simulations in the lab. Scientists across the globe are conducting groundbreaking experiments to recreate the extreme conditions of black holes right here on Earth. While we obviously cannot generate the immense gravitational forces of an actual black hole, researchers are using innovative techniques to mimic certain aspects, such as their behavior with light and quantum particles. One approach involves using ultra-powerful lasers to heat matter to extraordinary temperatures, creating plasma states that resemble the intense environments near black holes. Another fascinating technique uses supercooled atoms in a lab setting to simulate the effects of event horizons, the invisible boundaries around black holes where nothing, not even light, can escape. These studies aim to understand the mysterious interaction between quantum mechanics and gravity, a relationship black holes uniquely exhibit. By replicating these conditions, scientists hope to unravel questions about Hawking radiation, the theoretical process by which black holes slowly lose mass over time, and even the information paradox, what truly happens to the information that falls into a black hole. While these experiments are still in their infancy, they offer invaluable insights that might one day bring us closer to understanding how black holes could connect to the concept of time travel. And as research progresses, we may uncover answers to questions that have puzzled humanity for generations, stepping closer to unlocking the secrets of spacetime itself. Moving forward, let us dive into the fascinating concept of temporal causality and black hole feedback loops. Gravitational waves, ripples in spacetime caused by massive cosmic events like black holes merging, hold an intriguing potential to influence the flow of time itself. Some scientists propose that under specific conditions, these waves could create causal loops, self-contained paths where cause and effect become intertwined. Imagine a scenario where a gravitational wave's interaction with surrounding spacetime could, theoretically, send a signal that influences the very event which created the wave in the first place. This feedback effect is not just an abstract idea, it challenges our conventional understanding of time as a linear sequence of events. For example, could a gravitational wave shift spacetime in such a way that it alters the timeline of the observable universe? Some speculate that these loops might allow events from the future to impact the past, creating paradoxes where outcomes influence their own causes. Studying this phenomenon could open new doors to understanding how time behaves under extreme gravitational conditions, particularly near black holes. While entirely speculative at this stage, exploring these feedback loops deepens our quest to unravel the mysteries of spacetime and might someday lead us to extraordinary breakthroughs, perhaps even bridging the gap between the past and the future. Now turning to the concept of exotic black hole types, we encounter some of the most intriguing and speculative ideas in astrophysics. Among these are primordial black holes, which are theorized to have formed during the earliest moments of the universe, mere fractions of a second after the Big Bang. Unlike their massive counterparts, these black holes are thought to be much smaller, possibly no larger than a mountain or even a grain of sand. Despite their size, their intense gravitational pull could have profound implications for spacetime. Some researchers suggest that if these primordial black holes exist, they might serve as natural laboratories for studying the mechanics of time travel. Their unique properties could even help us probe the fabric of the universe itself. On the other hand, we have evaporating mini black holes, a concept tied to Stephen Hawking's groundbreaking theory of Hawking radiation. These minuscule black holes are thought to lose mass over time by emitting radiation, eventually shrinking and disappearing entirely. The process of evaporation raises fascinating questions about the nature of time near the event horizon. Could an evaporating black hole create conditions where time behaves unpredictably, offering glimpses into the possibilities of temporal distortion or even backward time travel. While no direct evidence for these exotic black holes has been found yet, their theoretical existence fuels our imagination and expands our understanding of how black holes might interact with time and space. Exploring these ideas not only deepens our comprehension of the cosmos, but also keeps alive the tantalizing possibility of uncovering new pathways to navigate time itself. Moving forward, let us delve into the intriguing connection between antimatter and the concept of time reversal. Antimatter, often described as the mirror image of ordinary matter, behaves in ways that defy our everyday understanding of physics. In certain equations, particularly those in quantum mechanics, antimatter appears to exhibit properties that can be interpreted as moving backward in time. This notion has sparked considerable speculation among scientists about its potential role in unraveling the mysteries of temporal mechanics. Could antimatter hold the key to reversing time? Some theories suggest that interactions between matter and antimatter could create phenomena akin to a temporal mirror where the flow of time is reversed. This idea becomes even more captivating when linked to the realm of black holes. The immense gravitational forces near a black hole might amplify these time-reversing properties of antimatter, creating scenarios where the arrow of time momentarily flips or bends. If such conditions exist, they could provide a unique framework for experimental time travel or even offer insights into the origin and fate of the universe. Although these ideas remain largely theoretical, the study of antimatter and its relationship to time continues to challenge and expand the boundaries of modern physics, reminding us of how much there is yet to uncover about the intricacies of time and the cosmos. Now turning to the fascinating concept of the simulation hypothesis, we delve into an idea that challenges the very fabric of our reality. This hypothesis proposes that our universe might not be the base reality we perceive it to be, but rather a highly sophisticated simulation created by an advanced intelligence. Within this framework, black holes could be viewed not as purely natural phenomena, but as intentional constructs within the simulation, designed to perform complex functions such as data storage or manipulation. The idea becomes even more intriguing when we consider time travel in this context. If our reality operates like a coded simulation, then the rules governing time and space might be programmable. In theory, manipulating this underlying code could allow for adjustments to the flow of time, enabling movement to the past or future, much like editing a digital timeline. Black holes, with their immense gravitational fields and mysterious singularities, may represent points within the simulation where this code is most susceptible to alteration. Some scientists and theorists speculate that the simulated nature of our universe might explain the strange and unpredictable behaviors observed around black holes, such as extreme gravitational lensing or the anomalies in the flow of time near their event horizons. If advanced civilizations had a hand in designing these constructs, they might also hold the capability to manipulate them, potentially using black holes as tools for traversing time or accessing alternate simulated realities. While this concept remains speculative and lacks definitive evidence, it invites us to question the very nature of existence and our understanding of time. Could the mysteries of black holes and time travel be rooted in the artificial architecture of a vast cosmic simulation? This theory continues to inspire scientific debate and philosophical contemplation, pushing the boundaries of what we believe to be possible. Moving forward, we come to an intersection of cosmic mysteries with the Fermi paradox and the concept of time travel. The Fermi paradox centers around a compelling question. If intelligent extraterrestrial life is statistically likely across the vast expanse of our universe, why have we not observed any signs of it? One intriguing theory suggests that advanced civilizations may have unlocked the secrets of black holes and time travel, operating on a plane of existence or timeline that we have yet to access or even comprehend. Imagine a civilization so advanced that it has mastered not just interstellar travel, but the manipulation of time itself. By utilizing the immense gravitational forces of black holes, such civilizations could possibly bend or surpass the rules of spacetime, effectively hiding from less developed species like ours. They might be using black holes as cosmic gateways, not just to navigate the universe, but to traverse timelines, effectively existing in dimensions or epochs entirely separate from our observable universe. This could explain their apparent absence. What if they are simply not here in the way we understand here, or now in the way we perceive now? Alternatively, it is possible that their mastery over black holes and time travel has allowed them to retreat into insulated pockets of spacetime, avoiding contact for reasons we cannot yet fathom. Some posit that such civilizations might deliberately avoid interaction with less advanced species to preserve the natural evolution of intelligence. Or perhaps they view our reality as uninteresting or irrelevant compared to the limitless realms that time travel and black holes might unlock for them. This possibility forces us to rethink our assumptions about extraterrestrial life and its interactions with us. Could black holes and time travel be the means by which advanced civilizations not only traverse the cosmos, but also strategically conceal themselves, explaining why the universe feels so eerily silent? It is a thought-provoking question that keeps the enigma of the Fermi paradox firmly in the realm of cosmic wonder. Now turning to the concept of the holographic principle, we venture into one of the most fascinating and mind-bending ideas in theoretical physics. Imagine for a moment that everything we perceive in the universe, every star, every planet, every atom, and even the fabric of spacetime itself, might merely be a projection of information encoded on a distant two-dimensional surface. This theory suggests that the three-dimensional world we experience could be comparable to a hologram, where the true reality exists on a flat cosmic boundary. Black holes play a central role in this concept. When something falls into a black hole, it is theorized that its information, the fundamental blueprint of its existence, is not destroyed but rather imprinted on the event horizon, the outer boundary of the black hole. This paradoxical idea reshapes our understanding of reality, as it implies that information, no matter how deeply consumed by a black hole, is not lost but preserved in some form. This revelation challenges the conventional perception of time and space as continuous, suggesting instead that what we interpret as flowing time might be an emergent property of this encoded information. The holographic principle raises thrilling questions. If our universe operates like a hologram, could this illusion of depth and time be manipulated? Could black holes be more than just cosmic phenomena, potentially serving as keys to unlocking the deeper structure of our holographic reality? Such possibilities push the boundaries of what we know and offer a tantalizing glimpse into a universe far more complex and layered than we could have ever imagined. Moving forward, let us explore the intriguing concept of tachyons, hypothetical particles that have captured the imagination of physicists and science enthusiasts alike. Tachyons are theorized to travel faster than the speed of light, a boundary that, according to Einstein's theory of relativity, serves as the ultimate limit for anything with mass. If these particles exist, they would defy our conventional understanding of spacetime, potentially opening a pathway to backward time travel. The logic is rooted in relativity. An object surpassing light speed could, in theory, experience time in reverse, creating the possibility of events being observed before their causes, a phenomenon that challenges the very fabric of causality. Now, how do black holes fit into this speculative scenario? Some theories suggest that the extreme conditions near black holes, with their intense gravitational fields and warped spacetime, might act as a natural laboratory for the creation or observation of tachyons. If tachyons could interact with these cosmic giants, black holes might serve as portals where faster-than-light travel becomes conceivable. This would not only revolutionize our understanding of time, but also blur the boundaries between past, present, and future. However, tachyons remain purely theoretical at this stage, with no experimental evidence to confirm their existence. Yet, the idea keeps driving scientific curiosity, inviting us to rethink the limits of physics and dream about the incredible possibilities that such particles could unlock. Could tachyons, if proven to exist, hold the secret to traversing time through the enigmatic nature of black holes? These questions continue to fuel profound inquiries into the universe's most mysterious workings. Now turning to the fascinating concept of black hole time mirrors, imagine a scenario where black holes don't just consume everything in their vicinity, but also echo back glimpses of the past. This speculative idea arises from the study of gravitational wave echoes, ripples in spacetime often caused by colliding black holes. Some physicists theorize that these echoes might do more than simply trace the aftermath of such colossal events. They could act as spacetime mirrors, reflecting information from a previous moment in time. How could this work? The theory suggests that the intense gravitational fields around black holes, combined with quantum effects near their event horizons, might create conditions where certain waves are bounced back instead of being absorbed. These rebounds could theoretically carry fragments of information, almost like a cosmic replay of past events. If proven, this phenomenon would not only give us a new way to study the history of the universe, but also challenge our understanding of how time and causality operate. Could these gravitational wave echoes be a way of looking into a cosmic recording of what once happened, preserved by the black hole's extreme environment? While the concept remains highly speculative, it underscores the black hole's unique ability to distort and manipulate spacetime in ways we are only beginning to fathom. The implications, as always, are mind-boggling, raising profound questions about whether the past is ever truly lost or if, somewhere in the depths of spacetime, it continues to resonate in the echoes of black hole interactions. What other secrets might be hidden within these enigmatic waves? From here, we delve into the final frontier, where human ingenuity and artificial intelligence are teaming up to unravel even more cosmic mysteries. Moving forward, let us explore how artificial intelligence is becoming a powerful ally in decoding the mysteries of time travel and black holes. Imagine the enormous complexity of simulating the behavior of black holes or modeling the effects of time dilation tasks that are nearly impossible for humans to calculate with precision. Artificial intelligence, with its ability to process vast amounts of data and identify intricate patterns, is breaking barriers in this realm. Scientists and researchers are using advanced algorithms to simulate black hole conditions, revealing how they distort spacetime and interact with matter and energy. For example, machine learning models can predict how particles might behave near a black hole's event horizon or simulate theoretical constructs like wormholes to test the feasibility of time travel. These simulations aren't just theoretical exercises. They are providing insights into real-world phenomena like gravitational waves, helping us understand their origins and consequences. Artificial intelligence also enables the analysis of data collected from observatories and experiments worldwide, data far too immense for traditional methods to handle. By identifying unique patterns or anomalies, artificial intelligence might uncover signs of phenomena we've yet to understand, such as events that could hint at the possibility of time loops or traces of exotic matter needed to stabilize wormholes. The collaboration between human ingenuity and artificial intelligence doesn't just amplify our ability to explore these cosmic mysteries, it's redefining the limits of what we can know. Could artificial intelligence be the key to unraveling not only how black holes warp spacetime, but also how we might one day bend time to our will? These questions propel us toward the next frontier in theoretical physics, where the line between science and science fiction continues to blur. Now turning to the moral and ethical implications of time travel facilitated by black holes. Imagine the profound dilemmas that could arise from humanity gaining the ability to alter the past or shape the future. At first glance, the idea of fixing past mistakes or preventing catastrophic events might seem like the ultimate gift to humanity. But what happens when the ripple effects of such changes spiral out of control? Consider the potential consequences of erasing key historical events or altering pivotal moments in personal lives. A seemingly small adjustment in the past could trigger a domino effect, fundamentally reshaping the present in ways no one can predict. There's also the unsettling question of who should have the authority to make these changes. Would time travel become a tool for the few, potentially abused for personal or political gain, or could it be governed responsibly in the interest of all? Equally concerning is the impact on free will. If the future can be shaped by decisions made through time travel, does this negate the natural course of human choice and responsibility? On a larger scale, tampering with the fabric of time might disrupt the delicate balance of the universe itself, introducing paradoxes or catastrophes that we cannot yet foresee. For instance, altering a timeline might create alternate realities or even lead to the collapse of existing ones. The moral weight of forcing such outcomes cannot be overstated. Beyond theoretical physics, the ethical questions surrounding time travel challenge the core of human values, our sense of identity, justice, and fairness. These challenges remind us that exploring the possibilities of time travel isn't just an intellectual pursuit. It's a profound responsibility that would require humanity to confront its deepest principles and priorities. As these complex issues unfold, they compel us to think not only about what we could do if time travel became possible, but also about what we should do. With these questions in mind, let us now turn our attention to what the future of time travel research might hold and how it could redefine our place in the cosmos. With the next phase of the journey in sight, let us explore the future of time travel research and the boundless possibilities it may unlock. As scientific advancements continue to accelerate, the pursuit of understanding time travel and black holes has transformed from speculative thought to an area of serious inquiry. Researchers around the world are delving deeper into the mysteries of spacetime, guided by cutting-edge technologies and groundbreaking theories. For instance, quantum physics and general relativity have already begun to converge in ways that reveal tantalizing glimpses of what might be possible. Scientists are working tirelessly to decode the enigmatic singularities of black holes, searching for answers to questions about spacetime distortions and whether they could hold the key to traveling through time. Laboratory experiments simulating black hole conditions, though currently in their infancy, are paving the way for unprecedented discoveries. These endeavors are not limited to understanding the extreme physics of black holes, but also extend to concepts like wormholes and the exotic matter required to stabilize them. Theoretical models are becoming increasingly intricate, offering new frameworks for how time loops or traversable pathways might one day become a reality. In tandem with this, artificial intelligence is revolutionizing the field, helping to simulate complex scenarios and analyze data at a scale unimaginable to previous generations. The insights gained from these simulations could unveil unexpected pathways to mastering time travel. Moreover, the exploration of cosmic phenomena such as gravitational waves and their interaction with black holes presents another exciting frontier. As tools like space-based telescopes and particle accelerators become more sophisticated, the observational data they provide may help validate or challenge our most daring theories. These advances are complemented by philosophical and ethical discussions that aim to guide humanity's approach to this powerful and potentially perilous capability. While the journey is fraught with uncertainty, the collective curiosity and ingenuity of the human spirit continue to drive us forward. What lies ahead is as mysterious as the cosmos itself, but one thing remains clear: the pursuit of time travel and black hole research is not merely a quest for knowledge but a profound exploration of our place in the universe, our understanding of reality, and the very essence of time itself. With the next phase of the journey in sight, let us reflect on the incredible theories we have explored together. From the warping of spacetime in Einstein's general relativity to the tantalizing possibilities of wormholes as cosmic shortcuts, we have ventured into the depths of human imagination and scientific inquiry. We've uncovered how time dilation near black holes might allow us to glimpse the future, or how rotating black holes could potentially unlock pathways to the past. We've dived into the enigmatic concepts of singularities, the multiverse, and closed time-like curves, each offering a unique perspective on the intricate dance between time and space. Along the way, we examined the role of quantum physics, exotic matter, and even artificial intelligence in pushing the boundaries of what might one day be achievable. Black holes, once thought of as cosmic enigmas, now emerge as potential gateways to entirely new dimensions, challenging our understanding of reality itself. Yet with each answer comes a flood of new questions, reminding us of how vast and mysterious the universe truly is. What if, hidden within the heart of these black holes, lies the ultimate key to mastering time? Could they hold the answers to humanity's deepest curiosities, or even the tools to reshape our destiny? These are the questions that drive us to continue exploring, learning, and wondering. If these ideas have sparked your imagination, we want to hear your thoughts. What do you believe lies at the intersection of time travel and black holes? Share your insights in the comments below. Don't forget to like this video, subscribe to our channel, and hit the notification bell so you never miss another journey into the cosmic unknown. Together, let's unravel the mysteries of the universe, one question at a time.